Okay, so now we're going to pick up with 5.3, Part 3, and we're going to learn how to write formulas for polynomial functions if we're given a graph. So the first thing that we're going to do is we're going to identify the x-intercepts of the graph to find the factors of the polynomial. And then we're going to examine the behavior of the graph at the x-intercepts to determine the multiplicity of each factor. Then we'll find the polynomial of least degree containing all the factors found in the previous step. And then we're going to use any other point on the graph. The y-intercept may be easiest to determine the stretch factor. So what's going to happen is we're writing an equation in this form right here. So a times the first factor times the second factor times the third factor, so on and so forth. And with the factors from the graph. So let's look at this one. So let's identify the x-intercepts. So we have an x-intercept at -3. We have one at -2. We have one at +3. And we have one at +4. So if we were to write these as factors, this is the factor x plus 3. This is the factor x plus 2. This is the factor x minus 3. And this is the factor x minus 4. So we're going backwards. So now once we have that, we need to think about the multiplicities. So -3 looks like it's going straight through, and it doesn't look very flat. So I'm gonna say that's to the 1. This one also is going straight through, so I'm gonna say that's to the 1. Straight through, straight through. So I think they're each to the first power. So multiplicity of 1 each. So if we add those multiplicities together, we get a degree of 4. And let's see, there are 4 zeros, so that works out for that. There are how many turns? 1 here, a turn here, a turn here, a turn here. So 3 turns. So if there's 3 turns, and n minus 1 is the number of turns, degree is 4. 4 minus 1 equals 3. That does work. So, so now we have the equation f of x is equal to a times x plus 3 times x plus 2 times x minus 3 times x minus 4. So then what we need to do is we need to pick one point and plug in for x and for y, or f of x. They say that the easiest point to plug in can sometimes be, if you have access to it, the y-intercept. So that's the point 0, -3. So I'm going to put -3 in for f of x. And then everywhere I see an x, I'm going to put in 0. So I'm substituting in the point 0, -3, and I'm going to solve. So I get -3 equals a times 0 plus 3 is 3, 0 plus 2 is 2, -3, -4. If I multiply that out, I get positive 72, I believe, because 3 times 2 is 6, and -3 times -4 is 12, and 6 times 12 is 72. So then we want to divide both sides by 72, and if we reduce that fraction, we get -1 over 24. So now that we know a, we can write our equation. Our equation is f of x is equal to a, which is -1 over 24, times the factors, x plus 3, x plus 2, x minus 3, x minus 4. And that worked out with multiplicity of 1 for each. Alright, so you guys try this next one, given this graph, see if you can write a formula for the function. And when you're finished, pause the video first, and then when you're finished, unpause it and we'll go over it. Okay, so first I'm going to identify the zeros. looks like we have 3 zeros. We've got x equals -1, x equals +2, and x equals 4. So this would be the factor x plus 1. This is the factor x minus 2. This is the factor x minus 4. So now the multiplicity, this is bouncing off. That's bouncing off. And it doesn't look very flat, so it has to be even because it's bouncing off. It's bouncing off the x-axis. So I'm going to guess that it's 2. The next one, it goes straight through, but it kind of flattens out. So for this one, it goes through, but it flattens. So that means it's odd, but it's probably bigger than 1 because it flattens out. So let's try 3. And the last one looks like it goes straight through, so it's going to be a multiplicity of 1 because it doesn't look flat. So it looks like I have f of x is equal to a times x plus 1 squared times x minus 2 cubed times x minus 4 to the 1. So let's just check a couple things. The degree is 2 plus 3 plus 1. So 2 plus 3 is 5 plus 1 is 6. It's even. And if you look at the end behaviors, it does show that it is even. Let's see, there are 1, 2, 3 turning points. So we're good there as well because the most number of turning points we could have would be 5 because 6 minus 1 is 5. Alright, so let's figure out a. So I'm going to plug in the y-intercept, which is the point 0, -4, and use that to find my a. So -4 equals a times 0 plus 1 squared times 0 minus 2 to the third times 0 minus 4. So -4 equals a times 1 squared is 1. -2 to the third would be -8. And 0 minus 4 is -4. So -4 equals a times -32. So I'm going to divide both sides by -32. Oh, I'm sorry, positive 32. Negative times a negative is a positive 32. So divide both sides by positive 32. We get a equals -1/8. A should be negative because the right side is pointing down. So our equation, or our function, is f of x equals -1/8 times x plus 1 squared times x minus 2 to the third times x minus 4. And you can rearrange it so it goes in order of exponents. -1/8 times x minus 2 to the third times x plus 1 squared times x minus 4. Okay, so one more thing, the intermediate value theorem. Basically, what this theorem says, you can read through this, but the basic gist of it is if we've got a point f of b right here, and then we've got another point f of a right there. If f of b is positive and f of a is negative, then that means that there's some point f of c that is a 0. So what it means is if you've got, if part of the function is positive, another point of the function is negative, that means you have at least one 0 between the two. Because, and it should make sense, right? Because if this is positive right here, and this is negative, in order for this graph to go from this negative to this positive, it has to go through 0. So Let me just show you what the theorem says. It's called the intermediate value theorem, and it states that let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, so that means one's negative and one's positive, then there exists at least one value c between a and b for which f of c equals 0. So there's at least 1 0 between the two. That's what it means. So let's look at this example. It says, show that the function f of x equals x to the third minus 5x squared plus 3x plus 6 has at least 2 real zeros between 1 and 4. So just the easiest way to do this is just to make a table of values. And I need to show at least 2 zeros, so I'm going to plug in numbers between 1 and 4. So what are some numbers between 1 and 4? Let's just say 2 and 3. So if I were to take, and I'm going to do f at 1, and so then you'd put 1 in for all the x's. So 1 to the third is 1 minus 5 plus 3 plus 6. So 1 minus 5 is negative 4 plus 3 plus 6. Negative 4 plus 3 is negative 1 plus 6, and we get 5. If we plug in 0, f at 0, we get 0 to the third minus 5 times 0 squared plus 3 times 0 plus, oh, I'm sorry. I'm plugging in the wrong thing. You're probably like, what are you doing? Okay. Next, if we plug in 2, so 2 to the third minus 5 times 2 squared plus 3 times 2 plus 6, we get 8 minus 5 times 4 plus 6 plus 6. So we get 8 minus 20 plus 6 plus 6. So 8 minus 20 is negative 12 plus 6 equals 0. Okay. So now we're going to substitute in 3. So here's at least 1 0. So there's 1 0 at x equals 2. So now let's substitute in x equals 3. And so this is taking a while. So let's borrow Desmos. So x to the third minus 5x squared. So if I do x to the third minus 5x squared and plus 3x plus 6. And then if I click the little gear up here, I can do a table. And so we wanted to plug in 3, and we wanted to plug in 4. So when we plug in 3, we get negative 3. And we plug in 4, we get 2. Move this over some. So we get 2. And so what that means is because this one is negative and because this one is positive, that means there must be a 0 in between. So that shows that there are 2 zeros, at least 2 zeros between 1 and 4. Now we can look here at the graph, and if you look between 1, which is right here, between 1 and 4, there are 2 zeros. There's one here, and there's one right there. Right there. So 2 zeros. So that's just illustrating what the intermediate value theorem did for us. All right, so you guys try this last one. Use the intermediate value theorem to show that there is at least one zero between 1 and 2 for the function 7x to the fifth minus 9x to the fourth minus x squared. Okay, so we want to find at least one zero, so really all we need to do is make a table of values and substitute in these two numbers here. And if we show that one answer is negative and one answer is positive, then we know that there's a zero in between. So I went ahead and I went to Desmos and I typed in this expression, and I want to make a table. And if you look, we can see that 1 is negative 3 and 2 is 76. Negative 3, 2 is 76. 1 is negative, 1 is positive, so that means there is a 0 in between. And again, you can always go back to Desmos and you can check and see that between the points 1 and 2, so between 1 and 2, there is a 0 right there. Okay, so I believe that's all that I have for 5.3. Let me know if you have any questions.